Pretty important and interesting. Let's do a little bit of math. Here's a fundamental problem. Suppose I'm trying to make a Tesla. I've got a camera, and I'm going to look out front, and I'm going to decide whether I'm about to ram into something or not. So what you've got coming in is probably 4K pixels, maybe 30 times a second. That's a lot of data. That's about 4,000 by 4,000 data points, each in 3 colors, many times per second. That's millions of data points. Now, no model at all could possibly process those millions of data points without taking a long time. And yet, you have, half a second before deciding you're about to hit something and you better hit the brakes. By the way, you have the same problem as a human. If somebody throws a baseball at your head will jerk out of the way within 50 milliseconds. Now, how did you do that? Your eyes are the same. You have millions of pixels coming in, all this data, and somehow your brain rapidly figured out that this is the important information and do something about it. And it does that by ignoring almost all the data. That is what you must do. This is technically called dimensionality reduction. You would all go insane if you tried to process all the data coming in. You have all these, I'm looking out here, there's 50 people in the room. If you see them all, worry about each facial expression, it'd be crazy, it'd drive you nuts. Your brain automatically sorts things into the important stuff and the unimportant stuff. The amygdala does this and other parts of the brain do this. It's absolutely necessary, and by the way, it's easy to exploit. There's a famous video, you can look it up on the web, where a psychologist has people looking at a basketball game, and he says, people, now count how many times the basketball gets passed from one person to another, and if you do that, he has a guy in a gorilla suit ride a unicycle right through the game, and nobody even sees it. And you won't see it either when you watch the video. It's amazing, because the point is, you focus on something and pay attention, and your brain ignores everything else. Even when it is outrageous and perhaps interesting, you're paying attention to something else. It must be this way, or nothing would ever work. You can't possibly process all the data coming in. What you want is to find the important data and ignore all the rest. That's what must happen here. And you can see why if you consider this. If I have 2 parameters, x and y, and then I choose random points, well, most of the points will be in the middle. Not very many will be on an edge. But suppose I have more dimensions, like 100, 1,000, 10,000 dimensions. And remember, 10,000 pixels is nothing. An image is probably these days 4K by 4K, 16 million pixels. So it's not at all unreasonable to say you probably have tens of thousands or millions of dimensions. Well, the point is, if I define an edge point as being within 1% of an edge, and I have 100 dimensions, then some of those points, then each one of those points has 100 numbers, so one of them is going to be on an edge. So all the points are going to be on an edge. That's what happens. You can count. I had 1,000 random points, and I counted how many of them are on the edge. In 2 dimensions, only 25 of them are on the edge, but by the time you're at 1,000 dimensions, they're all on the edge. Now, consider that I'm trying to trace out something. In fact, I saw a useful diagram back here. Let me bring it up. This will do down in the Eta Boost section. All right, so suppose I'm trying to fit this curve. I need to have, maybe 10 points along that curve to trace it out. I can't just have a point on the edge and a point on the other edge. I have no information about the shape of the curve. So if I wanted to model the shape of that curve, I need to have samples in the middle, but you will never have them. No matter how many points you measure, they're all going to be on one edge or another, so you're never going to get that trace of points through the middle. And this is because you're overthinking it. If I were to get those points in the middle, I would be modeling the entire reality from all that data. That is the problem I cannot solve. No matter how many points I measure and process, I could never, in fact, make a model of all the data coming in. But that's not what I want to do. I want to solve some other problem and pick only the data that really solves that problem. That's the message here. And so this is why you do principal component analysis. Principal component analysis is the mathematical way to decide what part of that data is important and what part we can safely throw away. So here, for example, we got this training set of handwritten digits we're trying to sort, and you say how many dimensions? Now, I have 784 dimensions here. These are 19 by 19 pixel images. So originally I have 784 dimensions, but how many of those dimensions do I actually need? And the answer is you decide how much of the variance you want to explain. You measure the variance in them, and you measure how much each of those parameters contributes to the variance. And if you think about it, if you plotted them in some high-dimensional space, they'd be a gas of dots, and you find like a plane that fits through that gas of dots and gets most of the variance where the variation goes along the plane, and there's not much deviation from the plane. So it really is like fitting a hyperplane in a high-order dimension. And the point is, you can get 95% of the variance with 154 dimensions instead of the 784 dimensions that came in. And that is just a matter of principal component analysis, which is just a matter of mathematically trying hyperplanes until you draw a hyperplane through the dots that follows the trend of the dots with the minimum deviation over to the side. So you can use that with a random forest. And so with a random forest predictor, using 100 training images and 10 iterations, we were able to find the best component analysis, and we found we were able to predict it with 23 parameters. We were able to achieve an accuracy of 85%. By out of the 784 data points coming in, we boiled it down to just 23 dimensions. And those, of course, each are some combination of those pixels. And this is moving in the direction of what I said before. It would really be better to actually follow the lines and make higher order features of those dots. There are combinations of those dots, just 23 combinations that do a pretty good job. And now you can say, I would like to get a visual description of what's going on here. So what I'm going to do is reconstruct the images, including only those 23 parameters. And if you do, this is what you see. This is the original image. This is what it is, keeping only the 23 principal components. And you can see it's distorted them quite a lot, but you can still tell what they are, and that's the point. This is all you need. This is probably what your brain is really giving you most of the time, is this kind of information. And studies of memory and eyewitness testimony bear this up. People don't have a photographic memory of the past. They remember just a few little points and they sort of fill in the rest from context. Anyway, so that's an important mathematical issue, why you must do dimensionality reduction. You can't possibly process all the data. You have to somehow process a small subset in order to get any reasonable performance. All right.